Hello, welcome to lesson number 43, part 1, alpha decays. Now the reason why I'm saying that, even though this whole section is alpha, beta, and gamma decays, is because it is rather long to do just as one presentation. So I'm going to break it up into 3 parts. The first part is going to focus on alpha decays, but it's also going to look a little bit about the background of how we understand radiation. Then the second part will be beta decays, and the third part will be gamma decays, which is actually quite short, along with some stuff about how we measure radiation. So, to start off, we discuss Henri Becquerel, French physicist who actually doesn't wake up one day and say, wow, I'm going to discover radioactive isotopes or something like that. But what happens is, late 1800s, he gets a rock from a friend of his that has a rather unusually high concentration of uranium. And it's like, hey, thought you might be interested in this. Take a look at it. Well, Henri Becquerel is doing other stuff at this time, and he's not terribly interested in trying to figure out stuff about this rock yet. Now, he has been doing some stuff with photographic plates. And photographic plates, think of really early days photographic film, where they were actually sheets of glass that had been dipped in chemicals and then wrapped in brown paper to protect them from exposure to visible light, because you'd use them to take pictures. Anyways, he puts the rock down on one of these photographic plates, and then later on kind of comes back and he's like, oh, I'm going to develop this photographic plate. I don't know if there's anything that I had done with it already. And what surprises him is he sees the image that you see there. He can see these ghostly outlines from the rocks that he had put down on top of the plate. So what he realizes is that if they are being exposed in a way similar to the way they would appear after taking like a regular photograph with visible light, there must be some form of radiation being emitted from those rocks that's at least similar to visible light. And the idea of radiation here is that the rocks radiate. They give off something spontaneously on their own. Now, about the only other thing that he really actively does with this, as far as, let's call it formal experiments, is he does observe that if the rocks are a distance away from the photographic plate and there's a magnetic field between them, perpendicular of course, he can actually make the radiation change the path it takes to get to the photographic plate. So it's acting kind of like the way we would think of charged particles, right? Anyways. The next people to come along on the scene are Marie and Pierre Curie. Now, both of them are just giants in the world of science. Marie Curie has one of the distinctions of being one of the few people to actually be awarded 2 Nobel Prizes in separate fields of study, one of them in physics and one of them in chemistry, and at a time when, to be honest, women were not necessarily as valued as scientists. So just amazing accomplishments that she had. But not saying Pierre was, just getting by on his looks or something. He was really quite a smart fellow also. Anyways, they decide that they want to do their own research into substances that radiate, this radiation thing that Henri Becquerel has seen. And they end up actually isolating 2 elements that had never been seen before. Polonium, named after Marie's homeland of Poland, and radium, because it's radiating radiation. Anyways, they do every test that they can on these elements. Every chemical reaction, every physical experiment, put them under huge stresses and everything, and it never stops them from emitting their radiation. So they come to the conclusion that radioactivity must have its source somewhere deep, deep within the atom, because it's got to be coming from someplace that they cannot have a direct effect on. Now, the other thing that is observed is that something weird is happening as this radiation is being given off. The elements are actually changing into completely different elements. This is a process known as transmutation. So there's got to be something happening during the emitting of radiation that's caused the nucleus of the atom to decay, to break down and lose some of its parts. And if we think about it, that would mean that it would have to be things like the protons changing, at least, because the protons, the number of protons in the nucleus, is what determines what element you're dealing with. Now, this might sound like something that the alchemists claimed they could do, and that's the picture that I've got for you here. The fellows that claimed that they could take like a useless, plentiful metal like lead and change it into gold. But nope, this is not just some sort of magic trick scam stunt thing. No, it's real. The elements actually do legitimately change. So that's something quite significant there. Now along comes Ernst Rutherford, and he's doing some experiments right around the turn of the century. And notice that this does mean this is before he comes out with his model of the atom. But when he took a sample of a radioactive isotope and put it in a lead box, he drilled a hole in the top so that the radiation could only have one direction to come out of. And then he put a magnetic field out there. Kind of sounds like what Henry Becquerel did. And he put photographic plates around the outside and watched to see where they fogged up. What he was able to see is that there were three distinct, separate, different forms of radiation that were being emitted. And he gave them the names of the first three letters in the Greek alphabet. Alpha, in pink there, that looks kind of like a letter A, but it looks a bit more like a fish swimming with its tail. Beta, which is a capital B but with a tail hanging off the bottom of it, and gamma, which kind of looks like a letter Y there, but make it a bit more swoopy, loopy looking at the bottom when you do it, almost like you took the alpha symbol and you kind of tilted it sideways so that the more rounded part is to the bottom. Anyways, you can maybe take a moment here, even pause this video, and think about how you would use the hand rules to figure out something about charges involved here. Now, if you're looking at it the way I'm looking at it, right-hand rule, third right-hand rule, would show why the alpha is being pushed to the right, which means it must be positively charged. Left third-hand rule would be why beta is being pushed off to the right, and gamma going straight through must mean that gamma has no charge. Okay, so we've got those ideas. Now what we're going to do is focus radiation. And there's a few ways that you'll hear this described, or that you'll know this is what we're talking about. We'll say things like an alpha decay happened. Well, that's what's happening in the nucleus. Things are breaking down. We'll talk about alpha radiation being given off, the actual radioactive or radiation that was being detected by these experiments that have been happening so far. And you'll also hear about the alpha particle. The alpha particle is what comes shooting out of the nucleus, and it is actually the radiation. So, what are the properties of this alpha particle? Well, we've already seen that it gets deflected like a positive particle in a magnetic field. And in fact, we know that it has a double positive charge. And that's why I do mention here that it's highly ionizing radiation. Because it has the potential to grab away two electrons if it comes near something. But really, alpha radiation, even though it's highly ionizing, is typically not that dangerous. Because if I had a sample of something sitting on the desk in front of me and I know that it emits alpha radiation, honestly, not an exaggeration here, I could put several sheets of paper over top of it and that would block all of the alpha radiation. Alpha radiation must be really big particles then if they can't even fit through sheets of paper. Even if I get rid of the sheets of paper, I'm still basically safe because the alpha radiation will be blocked by just the air between me and the source. I've got about a meter or two of air between us. No worries. The alpha radiation is being stopped by air. Even if I pick it up with my hand, I'm still okay because I have to remember the outer layers of skin on my hand are going to be dead skin cells, and you can't get sicker than dead. So those dead cells are blocking the radiation. The only way it can be dangerous is if I ingest it. if I take the source of the alpha radiation and I either swallow it or I breathe stuff in from it, because then the emission of the alpha particles is happening right next to my living cells. Now I've got a problem. So all I really have to do to protect myself, though, is just make sure that I wear something like a simple face mask, and maybe wear outer clothing that I'll dispose of afterwards, so nothing is left behind that I could somehow accidentally ingest. So why is it that this stuff has such a hard time passing through anything? Because it is actually rather big. Alpha radiation happens, the alpha decay in the nucleus happens, when the nucleus actually chucks out 2 protons and 2 neutrons together at the same time. Now I think about it. Hey, an alpha particle then, if it's made up of 2 protons and 2 neutrons, must be a helium nucleus. I know I say there helium atom. It should just say helium nucleus. That means it's helium-4, and it really genuinely is real helium. We can even write it that way if we want, but we usually use the alpha symbol because we're trying to remind ourselves of the importance that this is a particle that was ejected from a nucleus. But in this process of letting go of 2 protons and 2 neutrons, the remaining nucleus becomes smaller and more stable. And that's what a nucleus is always trying to do, is reach a more stable state. So how would I write this out? Well, I have to first of all know something that goes through actual alpha decays. So I'm going to use iridium-168 as an example for you. Now, this doesn't mean that you have to memorize this or something. You would either have a table of values given to you showing different isotopes going through different kinds of decays and what's happening, or maybe they give you some sort of a hint in the way they write out part of a decay for you. But you don't have to memorize like iridium-168 goes through alpha decays. I'm just flat out telling you that. And then I say I want you to write out the process for it. So what I should do for starters is look up at a periodic table. I take 168 divided by 2, so about 84, and I start looking from atomic number 84 backwards on the periodic table. And there we go. We find iridium. It's number 77. So I know what its Z and A values are. I also know that one thing for certain that's happening is that iridium releases an alpha particle. Notice the way that I'm writing this out. It does look like a chemical reaction, but we're not doing anything to the iridium-168 on the left-hand side. It goes through this alpha decay spontaneously on its own. So it's the only thing written on the left, and then the arrow is showing that, yeah, like a chemical reaction, we're about to show you what the products are. One of them is the alpha particle, and notice it's got the Z and A values 2 and 4, because that correctly describes what alpha is, 2 protons and 2 neutrons. And I also know that something else has to be left behind, because although the iridium ejected this helium, most of what was there is still left behind. So I've got to figure out what it is. For this, I use conservation of nucleons and conservation of charge. Conservation of nucleons is me looking at the values up at the top. I started with 168 nucleons. After the decay happened, so far I only know where 4 of them are in the alpha particle itself. So how many other nucleons must there still be? 164, because 164 plus 4 will give me 168. So now I know the A value of my unknown isotope that's been produced. And then I use conservation of charge. Now, what I'm saying here is that, at least right now, kind of a simplification of it is to think of it as making sure the total number of protons stay the same on both sides. But we are going to see that when we get to beta decays in the next part of this video lesson, that it really is conservation of charge. And we do have to look at that number on the bottom, the Z value, and say, well, it's usually protons. But we'll see we do some weird things there later with the beta decays. So right now, I know that I started with 77 positive protons. But after the decay, I can only see where 2 of them have gone, the release of the alpha particle. So how many others are left behind? another 75. So that means I can look on my periodic table for an element with an atomic number of 75, and I find out it's rhenium. So just look at those numbers. The numbers on the right add together, tops and bottoms, to give the numbers that I started with on the left. And this is a fundamental thing to always remember about any decay. Even if we show you something that you've never seen before, some weird, hey, we never learned this kind of decay, conservation of nucleons and conservation of charge will always work if you apply it correctly. Now, the other thing that we usually do here is we give some special names to this because we don't want to just, say, oh, it's what I started with and what I ended with, products and reactants or something, because that's like chemistry. So whatever we started with is referred to as the parent nucleus. Whatever we produced as the emitted particle, and in this case it's just an alpha particle, just keeps its own name. And then daughter nucleus is whatever we have as the remaining nucleus that's left behind that reached its more stable state. It's also worth mentioning that rhenium-75 is probably not the most stable isotope in the universe either. So a daughter nucleus can actually continue on to do other decays of its own after the fact. But we do get to another interesting little detail here. If we actually totaled up the masses, we would actually find that the mass of what we started with in the parent nucleus is heavier than the total mass of the alpha particle in the daughter nucleus we started with. The iridium is heavier than the alpha particle and the daughter nucleus. Now, is it a huge change? No, not at all. We are talking about things happening at a nuclear level here, but it is measurable. So what I can do is actually use the idea of conservation of mass energy to say that that missing mass, it didn't just vanish, it turned into something else, energy that was released. Typically, most of that energy is going to be the kinetic energy of the alpha particle shooting out really, really fast, and the daughter nucleus going in exactly the opposite direction, which, by the way, if you have enough information, means you can also do conservation of momentum with them, because you would assume that the parent nucleus was at rest at the beginning. So if you know enough information to get masses and velocities of the alpha particle and the daughter nucleus, you can totally do a 1D conservation of momentum question here. Now, it is worth also noting that because the alpha particle is much lighter, it's going to be going much faster, typically, than the daughter nucleus, which is typically going to be something relatively big, probably. Oh, and I'd already mentioned that part, sorry. So, we're going to look at how we would measure the energy released during the decay of uranium-238 to thorium-234. Now, uranium, you can probably find pretty fast on the periodic table because it's the largest, biggest naturally occurring element. So you look there, look just a couple steps back, and you'll find thorium. Now, what I should notice is uranium-238 decaying to thorium-234. If I do all my conservation of nucleons thing, the only thing that would balance all of this out is if an alpha particle was also being emitted. So there's my decay equation, and we can see that starting with uranium-238 and releasing or having at the end thorium-234 meant that I must have had an alpha particle release during this decay. So again, this is where I don't have to tell you it's an alpha decay if I gave you enough information in the question that the only thing it could be would be an alpha particle. Now, if this was on a test or something, or even a diploma, we'd probably give you a chart with a bunch of atomic mass unit weights of these different isotopes, but I'm just going to find these masses in the back of our textbook on page 881. And when I look there, I'll see that uranium-238 has a mass of 238.0508 atomic mass units. My alpha particle, really is just a helium nucleus. It's 4.0026 atomic mass units, and thorium-234 is 234.0436 units. Now what I'm going to do is take those two numbers on the right and add them, and that's when I can see that what I started with is heavier than what I ended with. So what do I do with those two numbers? I subtract them from each other, and I find out that the missing mass is 0.0046 atomic mass units, which is very small, but that's why we need all these extra sig digs here, much more than we usually deal with, because that's going to be where we see the change in mass occur. But that really is delta M, that's a change in mass, so delta E, the real way that we should be thinking of E equals mc squared, I can convert that into kilograms, and I'm just using the conversion that's on the data sheet that shows one atomic mass unit is 1.66 times 10 to negative 27 kilograms. You'll quite often find that in lots of questions will give you a more precise, more sig digs value than that conversion. If we give you a number with more sig digs that's more precise, you use it. You don't say, oh, I'll just go back to looking at the data sheet. If we're giving you more precise numbers in a question, we're doing it on purpose. We want you to use the numbers that you're being given, not looking at the slightly worse numbers on the data sheet. So I've got the mass in kilograms. I'll grab E equals mc squared and throw it in, and I get 6.8724 times 10 to the negative 13 joules. That's not very many joules. I think it would maybe be better if I changed it into electron volts. So I use the conversion from the data sheet, and I convert it to 4.30 times 10 to the 6 electron volts. That's still not so great, because I've got a number in joules that's pretty small, and I've got a number in electron volts that's pretty big. But hey, 10 to the 6? That's mega. So this is really 4.30 mega electron volts. And what we find is a lot of the measurements that we take when we're doing this sort of stuff, they end up actually looking pretty good in a mega electron volts. So even if this was 10 to the 7 or 10 to the 8, I could write a number that's in the tens or hundreds of mega electron volts, and it's actually a more reasonable way of seeing it. We just have to recognize that if we're given a number in mega electron volts, we have to change it back to like 10 to the 6 electron volts, and probably even then change that back into joules before we continue with any other calculations. Now that's going to be the end of this first part of lesson 43 on alpha, beta, gamma decays. Remember, there's going to be two other parts on the beta decays and gamma decays that you can also look at. Good luck.